I'm here with Dr. Romano to do the second half of the 2009 ADA organic exam.
Hi, I'm Dr. Romano. I'm professor of organic chemistry here at Romano Scientific and the creator of the OrgoMan products and the author of the Dot Destroyer book. I'm working on the second part of these questions, which I think are very, very easy, and hopefully you're enjoying it. And if you got questions, you can hit me up on the study group. So come along and let's continue on. Okay. On this problem, number 87, it says in this reaction, what's the major product? Once again, it's an alkene, and we're treating it with either HCl or something like that. So I'm thinking one word, Markovnikov. Now, I want you to watch as I go off to the side. We're only going to do a little step, and what I'm going to do is I'm going to add an H to the carbon with the most H's and form a carbocation. So when I do that, watch. Now, anytime I form a carbocation, I look for a shift. Here I don't see any shift because this is a tertiary. So that means that the Cl minus can come in and then attack. And if it does, that would be choice letter C. That's a very, very easy problem. Okay. Number 88. What we're going to do is the reaction of, this is ethyl magnesium bromide with acetone, followed by the hydrolysis of dilute acid. Well, this is going to be a simple reaction called a nucleophilic addition. So we're going to write out the ketone, and then I'm going to write out the CH3, CH2, MgBr, and then acidify it. All you do is get your fingers, cut the double bond. The double bond cuts. You make it into an OH. There's the CH3. And then you add this group on, and you would get this tertiary alcohol. And if we just go hunting, it's a tertiary alcohol with two methyls and an ethyl. That would be choice letter C. Very easy. In the Destroyer book, we have many more challenging questions, like when a Grignard reacts with an ester, for example, or reacts with an acyl halide, and that would give me a tertiary alcohol. It's a little more challenging. All right, at any rate, here's a good one. Which reaction is an example of a terminating step? Terminating step, first of all, is an exothermic step. So we want to make sure we know terminating steps. Number one, terminating step is an exothermic step, and two, the energy of activation of a terminating step is approximately 0. And what we're going to look for is two radicals colliding, and that's shown in letter C, two radicals colliding. Choice B, that would be the initiating step, and that would be the most endothermic step. You may thank me for that someday. And then when a radical attacks a neutral molecule to give a new radical, as you can see in letter A, or you can see in letter letter D, or in this one, they all end up giving new radicals. These will be propagating steps. But choice C, there's our terminating step. Number 90, this is very easy. A bromine is an OP director, like all halogens. They direct OP, but they slightly deactivate the ring. A little bit, going to be slower than benzene, but it's going to direct it ortho and para. There's more bias towards the para isomer, and you would get 1 bromo, 4 nitrobenzene in letter C. That was a very easy problem. All right, next. On this group, on 91, all we want to do is to go from a CH2OH into a COOH. We're going to simply oxidize it. Whenever you oxidize something, look for something with a CR or an MN in it. MN like KMNO4, or something with CrO3, chromic acid. So that's a slam dunk. If you go to the Destroyer book, I have a lot of new questions in our new edition on a very new methodology known as a Swern oxidation that I need you to look at. All right. Number 92 is a sure bet question. This is a standard question on ozonolysis. And it says that some compound was hit with ozone, then zinc and water, and it gave these two products. And these two products would be, this is called a propanol and 2-butanoate. I think the easiest way to do it is, why don't you just go to the wrong answers and simply work it backwards? So why don't I just go right to B? If you cut B down the middle, and when you cut it down the middle, you simply, so in other words here, let me go off to the side and show you. You got CH3, CH2, CH, then you got CH2, CH3. So all you would do is say two words, actually three words: cut and oxidize. So if you cut it, after you cut it, you simply put in the double bond O, and you would get the propanol and the 2-butanoate, and that would work. None of the other ones would work. So I'll leave for you. If you go to the Destroyer, you can see other more exotic ones. But if you understand that, you're in good shape. I'm going to show you a quick way to do number 93 to cut the bullshit out, so you don't even have to think. It says the two Brunster-Lowry bases in equilibrium below a blank. The minute I see HOAC, you should automatically know HOAC is acetic acid, and HCN is hydrocyanic acid. The minute you see the guys with the sodiums, you know they're going to be bases. So obviously the answer here has got to be choice C, the two species with the sodium. We'll keep that question real simple. There's no variation. You would have to be very, very clever to make up a question where you would have sodium on a compound in which the answer wouldn't be basic. For you, that'll be fine. On 94, the most acidic proton. This is a slam dunk. First of all, this carbon here is an sp3 carbon, and those H's are not acidic. You would have a pKa up around 50. And alcohol has a pKa around 16. So alcohol's around 16. If you are next to a carbonyl group, maybe somewhere around 16, 17, but an H off a carboxy group comes in around 5. And if you go off to the side here, you can see why. Why is a carboxy acid acidic? Because when you remove the H, you get an anion, and as you can see, this anion is able to do resonance. Now, I know you might say to me, well, big deal, it could do resonance. No, not a big deal. Resonance allows me to spread out the negative charge. And if I can spread out the negative charge, I can stabilize the anion. So therefore, the answer would be choice A. All right, next. On problem 95, we want to know the conjugate acid of para-aminophenol. Well, as you look here, you got an alcohol group and you got an amine group. I tell all my students never to forget these three words: amines or bases. So that means if an amine is a base, that means it's going to want to accept a hydrogen. So as you can see, the conjugate acid comes from the group that was basic, that picked up an H, and as you can see, that would be choice letter C. This would be the conjugate acid. If I would have asked what's the conjugate base of this, then the conjugate base of this, well, if you go back to the original, an amine is a base, so it's not going to want to lose an H. But an alcohol, a phenol has a pKa of around 10, so this would be the structure of the conjugate base. But this would be the structure of the conjugate acid. All right, on 96, it says the structure below is shown without complete geometric detail. What is the correct assignment of the bond angles? A is hovering right over a triple bond. We all know a triple bond is 180. And the double bond in B, that's an sp2 area where A is sp. So A is going to be 180. And anytime you're hovering over an sp2 region or here, it would be the 120 trigonal planar. So the answer is choice D. A would be 180 and B would be 120. 97, which is stabilized by resonance. Now, first of all, None of the other ones make sense. If you looked at choice A, for example, you got this. These electrons can't go anywhere. They're not able to move. And I can make that same argument for all of them, but if you look at choice D, and if you look closely, I drew the arrows for you. This would move down, and this would move out. That would be one resonance form. And then I can move this here and this out to give this. So choice E would indeed have resonance forms. That was a real easy question. Okay. And then finally, 98. What I want to know is which of the following is aromatic. I got some good questions on this in the Destroyer. But in order to be aromatic, first of all, you need to be cyclic. You need to be planar. You must have all the atoms able to delocalize the electrons. So it must be, another way to say that is it must be fully conjugated, and it must contain what we call a Huckel number that follows the pattern of 4n plus 2. So if you ever see anything with 2, 6, 10, 14, 18, or 22 electrons, you know it has the potential to be aromatic. For example, if I drew these two, you can see that this would have 6, it's cyclic, it's planar, and fully conjugated. This would also, this is a very commonly asked question, a cyclopropenium cation. Notice the electrons could move because whenever you got a positive charge, there's an empty orbital up here, and therefore it would be 2 pi electrons. So if you go to here, you can see that choice E, right off the bat, would be the correct answer. This would be pyridine. If you look here, and I gave you this, I did a video on this actually. This is 6 pi electrons. You don't count this because this is in a different plane, other than the plane of parallel p orbitals in the ring. This guy is not conjugated. This 2, 4, 6, 8, this says 8. It's not a Huckel number. And by the way, if you look at one of my videos, I show you that if you get an 8 and it's a cyclooctatetraene, this would actually be non-aromatic. Why non-aromatic? Because it's shaped like a tub and it distorts from planarity. B is not even cyclic, for God's sakes. And then A is anti-aromatic because it's got 4 pi electrons. So if you ever see a 4 or an 8, that's usually anti-aromatic, unless you see something that looks like a stop sign, and that's non-aromatic because it's shaped like a tub. All right, the last two, what we want to do is complete the sequence. You're going to take the benzoic acid, and you're going to first treat it with thionyl chloride, SOCl2, and that would give the ACl halide. And then it says to take it with ethanol, HO, CH2CH3. All you do is split off HCl, and let's see what that gives me. That gives me this. And we're going to see if you guys can name this. I hope you could. We got some good questions like this in Destroyer. This would be ethyl benzoate. And the little fella would be on B. And then, last but not least, would be, what would be the final product? All we're going to do on this one, I don't know what happened to all the other choices, but I know one of them is here, so we're going to reduce this down. It's not so easy to reduce down to carboxy acid, but you could reduce it down with lithium aluminum hydride, and that will give you benzyl alcohol, and when you treat it with HBr, you would simply protonate it, form the carbocation, come in, and you would get benzyl bromide, which will be our only choice, whatever the other choices were, but they were all wrong, and there you go. I hope this helps. I'm going to be doing many, many more videos on all the other ones, and it'll be all free, so save your money on any subscription. I'll do it all for free for you. All right, good day to you. I hope you enjoyed, and that's how we got our 30. Bye-bye.